Hi, you guys. This is Mr. Pinter, your EE330 instructor. This video lecture covers part 2 of our first chapter on semiconductor basics. So in part 1, we covered these first few topics here, and in this second part of the chapter, I will be covering the topics that are highlighted here. So let's start with drift current and mobility. So in semiconductor physics and theory, there are two different types of currents that we have to deal with. In other words, electrical current can flow by two different mechanisms, and those mechanisms are called drift current and diffusion current. So drift current is when electrons or holes drift under the influence of an electric field. So for example, if we have an electric field that's pointing to the right in this diagram here, and we have a bunch of electrons in the area, all right, these are conduction electrons in the semiconductor. Well, the electrons, because they're negatively charged, they're going to move to the left, so that's the direction of electron flux. But remember that electrons, because they're negatively charged, the current is defined as the flow of positive charge in electronics. So the electron current is to the right. And this is just one of the kind of, unfortunate and confusing things that we have to deal with when we talk about current. Whenever there's electrons involved, the actual current that we define is going in the opposite direction as the flow of the electrons. The other type of current that we're going to cover in the next section is called diffusion current, which is very different. In diffusion current, electrons or holes diffuse from a region of high concentration to low concentration. So it is a gradient in the carrier concentration which drives the diffusion. So in this little diagram here, on the left side, we have a whole bunch of electrons, a very high density of electrons. And on the right side, we have a very low density of electrons. Now, these electrons are going to be moving randomly, in all directions. But because there are so many more electrons over here on the left, there is going to be a net flux of electrons to the right. So electrons or holes will always flow from where there are lots of them to where there are fewer of them. And, there are lots of analogies of this. One of them is when you think about traffic coming from a big city like Los Angeles, and then you've got a little suburb, over here somewhere else near the city, the number of cars leaving the city will always be greater, than the number of cars going into the city, just because there's so many more cars, in that type of example. So that's what diffusion is all about. It's random motion, but because of the difference in populations, the net flow will always go from high concentration to low concentration. And again, since these are electrons in this example, the electrons are moving to the right, but the electron current is moving to the left, again, because of those electrons' negative charge. So let's talk about the drift current now in more detail. So the drift current is due to, well, there's a couple of concepts that we need to take care of, and that is drift velocity and something called carrier mobility. So, remember the idea is that free carriers, electrons and holes, move in response to an electric field applied to them. And, this is just basic physics that you learned, back in your physics classes. An electric field causes a force on a charged particle. So again, if the field's pointing to the right, electrons will feel a force going to the left because of their negative charge, and holes will feel a force going to the right because of their positive charge. So the two carriers, in this picture here, would be pushed in opposite directions. And this motion is called drift. So electrons and holes drift in the presence of an electric field. And the speed at which they move is called the drift velocity. That makes sense. And so we have V for velocity and D for drift. So it turns out that the drift velocity is proportional to the amount of electric field that's present. And that makes sense. The stronger the field, the faster those particles are going to drift. And sort of the constant of proportionality in here is given by the Greek letter mu, and mu is called the mobility of the electrons and holes. So if we look at a graph here, this is a graph of drift velocity. Notice it's log scale, so it's several orders of magnitude, plotted as a function of the electric field, which is, remember, the electric field is the force that's pushing those particles. So not surprisingly, as we increase the electric field, the drift velocity of the electrons and the holes increases because there's more force. Now, the slope of this curve, if you think of this equation here as a linear equation, this is like y equals mx, right? This m is the slope in algebra. So the slope of this graph is the mobility. All right, and it literally, is the graphical slope of this graph. Notice that electrons have a higher drift velocity than holes. All right, and so electrons typically have more a higher mobility, and we'll see this in more detail shortly. The other thing I'll just point out here is something we're not going to deal with too much in this class, but at really high fields, what happens is the electrons and holes, they don't continue to go faster. They start knocking into all the atoms in the silicon crystal, and they have to, they reach a limit of how fast they can go. And this is called the saturation velocity, and it's around 10 to the 7th or 10 million centimeters per second. So let's just go a little further now with these concepts of drift current and mobility. So we know that the electrical current is proportional to the number of carriers present. And this is because, remember again from basic physics, the current is defined as the amount of charge that flows per unit time. So sometimes it's shown, as dq dt, right? The rate of change of charge flowing across some point. So certainly the more electrons we have present, the larger the drift current will be because the Q, the charge, is greater. Now, we also learned that current is proportional to the electric field strength, and this is because the field creates the force that pushes these electrons. And the current is proportional to this constant called the carrier mobility, mu, which describes how fast the carriers move under the influence of a field. So technically, mobility is the velocity, the amount of velocity per unit of electric field strength. So putting this all together, we see that the drift current density, now remember from physics, J is the letter that's used for current density. Current density is current per unit area, and I is used for current, okay? So the current density, J, for electrons, that's J sub n, is proportional to n, remember that's the concentration of electrons, the number of electrons, E, the amount of electric field, the strength of the electric field, and mu sub n, this is the carrier mobility for electrons. And Q is put in there because Q multiplied times n gives us the number of charge. Q is the charge per electron. And I should have put that in here, but again, remember from basic electrostatics and physics, you learned this probably a couple years ago. The charge of an electron is 1.6 times 10 to the minus 19 coulombs. So Q is a constant that shows up a lot in semiconductor device physics theory. So this expression here tells us how to calculate the drift current density. All right, it's the electron charge times the mobility times the concentration of electrons N times the electric field strength E. Likewise for holes, the drift current density is Q times the hole mobility, mu sub P, times P, which is the hole concentration, times the electric field strength again. So this graph here, we'll look at this in a little more detail soon, is a graph showing the mobility. All right, this is, remember, that's that mu inside the equation there. Mobility as a function of doping density. So mobility is not really a constant. It varies greatly with the doping density. So notice for electrons, for example, for lightly doped materials, all right, where there's not a lot of dopants, The mobility is very high. It's about 1400. All right, and the units here are, centimeters squared per volt seconds. But as we increase the doping density, the mobility drops. And the reason for this is that the electrons are scattering off of the ionized dopants. So remember, when we put some dopant like phosphorus, let's say, or arsenic in a semiconductor, those dopant atoms become ionized. They donate an electron and they have a positive charge because they're ions now. Well, those ions, those ionized dopants, cause electrostatic Coulomb scattering of the electrons. All right, so the electrons, instead of being able to just, drift right through the semiconductor, they're bouncing around and getting, deflected and scattering off of all those carriers. So the higher the doping, you can see the mobility drops to, something like 150 for really heavily doped silicon. And holes shows, the hole mobility shows a similar behavior. Hole mobility is less than electron mobility. It's somewhere, looks like a little around 500, something like this for lightly doped silicon, but it also drops with doping density. Let's now take a look at resistivity and conductivity. So resistivity and conductivity has to do with the material properties of the semiconductor. And this is something else, again, that you learned back in one of your physics classes where you studied basic electrical properties of materials. If you have a block of some sort of conductive material here, it could be a metal, it could be a semiconductor. Okay, we're going to obviously be working with semiconductors. But whatever this material is, let's say it's a rectangular block here, and it has, we connect it to a battery. So we have a positive voltage over here, and we ground the other side over here. So this block of material has a length of L, and it has a cross-sectional area of A. So this block has a specific resistance to it. And of course, you're familiar with Ohm's law, V equals IR. So this block behaves as a resistor. So the resistance of this, this material, this chunk of material here, is proportional to L and inversely proportional to the cross-sectional area A. So what that means is if we have a longer block of material, there's going to be more resistance because the current has to go and travel through a longer distance through this resistive material. Conversely, the cross-sectional area allows more current paths to go through. So the larger this cross-sectional area is, the lower the resistance is. Okay, so resistance has L on top, the length of the resistor material, and it has cross-sectional area A on the bottom. The sort of the constant of proportionality in here is called rho, and that's a Greek letter rho, and rho is called the resistivity of the material. It's a material parameter, and different materials obviously have different resistivities. Metals have very low resistivity. Insulators have extremely high resistivities. Semiconductors are kind of in the middle, and we're going to develop an equation to figure out what the resistivity is, which is going to depend on the doping of the semiconductor. But anyway, the resistance of this piece of, chunk of semiconductor here is equal to rho times L divided by A. Now, one thing we can do here is we can take Ohm's law, V equals IR, and we can substitute rho L over A in for R, the resistance. So we get V equals I times rho L over A. Now we're just going to kind of do some tricks here and move some things around. Let's take the L and let's divide both sides by L. So on the left I have V over L, and on the right I have rho times I over A. Well, the voltage across this piece of material divided by the length of the material gives us the electric field across the material. If you remember again, we're relying a lot here on what you learned in physics back in, when you studied electricity in physics. So if you're rusty on that, you might want to review some of these basic concepts. But remember, an electric field is how many volts per centimeter, okay, or volts per meter, depending on the units. We're going to be using centimeters. So V over L just gives us the electric field strength in volts per centimeter. And likewise, current per unit area, all right, I over A, that's J, which remember is current density. So this kind of simplifies to E is equal to rho times J. If we solve this for J, we can divide both sides by rho. We get J is equal to 1 over rho times E. And 1 over rho, 1 over the resistivity, is called the conductivity, which is given by the Greek letter sigma. So conductivity and resistivity are reciprocals of each other. That makes sense. The more resistive a material is, the less conductive it is, okay, and vice versa. So anyway, this equation here now becomes this right here. J is equal to sigma times E. So this is, even though it doesn't look like Ohm's law up here, you know, you learned V is equal to IR in your circuit class, this is another way to express Ohm's law in, you know, more advanced textbooks. J, the current density, is equal to conductivity times electric field strength. Okay, so let's continue on from what we did on the last slide. So we learned that, you know, we can sort of dress up Ohm's law and restate it as J equals sigma E. The conductivity then, sigma, you know, from this is equal to J, the current density, divided by the electric field strength, E. So we know that the total current density, we're talking about drift current here, all right, is J due to holes, that's JP, plus Jn, which is drift current due to electrons. And these are the two expressions for drift current that we derived a couple slides back. Remember, it has the mobility, the hole density, and the electric field strength. And likewise, there's a same term over here for electrons. So if we look at this expression here, sigma, the conductivity of a semiconductor, is equal to J, which is all of this, divided by E. So we can cancel out these E's here. And we're left with our result here. The expression for a semiconductor's conductivity, sigma, is given by, and I factored out the Q, it's Q times quantity mobility of holes, mu P, times hole density, plus mobility of electrons times electron density, all right? And and remember that sigma is conductivity, which is 1 over the resistivity. So the units of conductivity are 1 over ohms per centimeter. And when you have 1 over ohms, there's a couple different ways to show that. They sometimes show it as an omega symbol, you know, which means ohms, right? But it's upside down, so that tells us it's the inverse of omega. That's also called a mho. All right, and if you notice, mho is just ohm spelled backwards. All right, so these are just a couple of clever ways to describe conductivity. It's mhos per centimeter is the unit of conductivity. And then finally, we can go back and calculate semiconductor resistivity, rho. Remember, rho is just 1 over sigma, and so it's just 1 over this result up here. And so that's what's shown here. And the units for sigma are ohm centimeters. Notice that's the reciprocal of mhos per centimeter. All right, and so resistivity, you can see, is going to let's take a look at conductivity. The more holes or the more electrons we have, the higher the conductivity. All right, that makes sense. There's just more charge carriers. Likewise, for resistivity, the more holes or electrons we have, that's going to lower the resistivity because it's down here in the denominator. So this is a plot showing, we're actually not going to use this one. We're going to calculate these things a little differently, but this is a log-log plot showing the resistivity of a semiconductor as a function of the doping level. And you can see, as we increase the doping level, the resistivity drops lower and lower because of this relationship here. Okay, so we can put all of this together by doing an example. And this is the type of example that you're going to see in the first homework. And so this sort of summarizes all of the concepts we learn. So in this problem, we have a piece of silicon that's doped with antimony at 1 times 10 to the 16 per cubic centimeter. And it has the dimensions shown. All right, so here's, it's 5 centimeters by 2 by 2 centimeters. And it's connected to a 12-volt battery. So the problem asks us to find the conductivity, resistivity, resistance, current density, and current flowing through this piece of silicon. All right, so that's quite a bit, right? We have to calculate quite a bit of things. So let's start with what we know. Well, we're told the semiconductor is doped with antimony. So antimony, chemical symbol Sb, if we look back on our periodic table, antimony is in column 5. That makes it a donor, right? It has that extra electron. So the number of electrons in this semiconductor is going to be equal to the doping level, which is 10 to the 16th, okay? And because it's doped, with so many antimony atoms, N is high, we can ignore the number of holes, all right? Remember the law of mass action, N times P is equal to Ni squared. Well, if you calculate the number of holes for the number of electrons equal to 10 to the 16, it's going to be a very small number compared to the number of electrons. So we can ignore the holes. The holes play no part, no role in determining the resistance or any other properties of this piece of semiconductor. Now, if we go back, I can't flip back here in this video, but if we look on a couple charts ago, or a couple slides ago, if we look at a doping level of 10 to 16, we'll see that the mobility is around 1200. Okay, so that's what we're going to use for mu. So here is our, the first thing we're going to do is calculate conductivity. So here's our expression for conductivity from the last slide. Now remember, we don't have to include the holes here. We can just assume it's 0 because there's so few holes compared to all those electrons. So the conductivity is going to be approximately equal to Q times mu times N. And mu, well, let's start with Q. Q, again, is the electron charge, 1.6 times 10 to the minus 19. Mu is, given right here. It's 1200, all right? I have to save room. I didn't include all the units. And N is the number of electrons. We, calculated that up here. It's just equal to the doping density. It's 1 times 10 to the 16th. So if we multiply these numbers together, we get 1.92. And remember the, kind of odd units are mhos per centimeter for conductivity. All right, so we're done with the first part. Now, to calculate the resistivity, well, that's easy. Resistivity is just 1 over the conductivity. So we just have 1 divided by 1.92 mho per centimeter. And 1 over 1.92 is 0.52. This mho down here, gets flipped because it's on the bottom, so it becomes ohms. And this centimeter, to the -1 power goes to the top, so that becomes centimeter. And as always, resistivity has units of ohms centimeters. Okay, so there's our answer to the second part. The third part was calculate the resistance of this. How many ohms is this chunk of material? Well, here we can use our formula for the resistance of a material. It's equal to rho, which is the resistivity, times L divided by A. And so we know what rho is. We calculated it here. We know what L is. It's given, right? The length of this thing is 5 centimeters. And the cross-sectional area is 2 times 2, which is 4 square centimeters. All right. And so what you have here is these centimeters up here cancel the centimeter squared down here. And we end up with 0.65 ohms. So that's the resistance of this block of material. All right, next thing, calculate the current density. So remember that we can state Ohm's law in sort of this, odd form here. Current density, J, is equal to sigma times E. All right, we derived this a couple slides ago. So we know all these numbers now. Sigma is the conductivity, 1.92, right? We got that from up here. And the electric field, well, remember, we can calculate that very easily. We've got 12 volts from this battery, that is seen across 5 centimeters. So the electric field is 12 volts divided by 5 centimeters. And I can't do that in my head, but it looks like it's going to be about, 2.4 or something volts per centimeter. But when you do this on a calculator, you'll come out with a current density of 4.61 amps per square centimeter. Finally, what is the current that flows through this circuit, right? The current's going to go around here from positive side of the battery through the material and so forth. Well, there's a couple ways to calculate this. One of them is, remember that current is equal to the current density times the area, all right? And so we have 4.61 amps per square centimeter multiplied by the cross-sectional area, which is, again, 4 square centimeters, and you get 18.4 amps, or you can just use Ohm's law, right? Ohm's law says that current is equal to voltage divided by resistance. So the voltage would be 12, and the resistance would be right here, 0.65, and if you plug that into your calculator, you'll get the same answer of 18.4 amps. So we've looked at drift current and mobility. Now we're going to look at the other type of current, that is diffusion current, and that will lead us to something called diffusivity. So remember that diffusion current is not proportional to the number of carriers present, but it's proportional to the differences in the carrier concentration. So in other words, diffusion current is proportional to the carrier gradient, all right, or the gradient in carrier concentration. So if we can use calculus and think of, for electrons, we're talking about dN dx, right? This is the rate of change of electron concentration with distance. Okay, so this is the slope, in other words, of the electron concentration. Likewise, for holes, dP dx gives us the slope of the hole concentration. Okay, so we've seen this diagram before. Remember, the main idea is if we have a lot of electrons over here and we have a few electrons over here, the electrons always flow from high population to low population. So electron flux is going to be to the right, but because they're negatively charged, the electron current will be pointing to the left. Now in this example, this plot over here, this is showing a plot of P, which is hole concentration, as a function of position. So notice in this graph here, we've got holes, very few holes over here, and we've got more holes over on the right side. So, the slope of if we want to calculate the diffusion current at any given point here, all we have to do is calculate the slope of this gradient here, right, of this profile. That's dP dx. And also remember that the holes are, in this example, are going to diffuse to the left. They always diffuse from where there's more holes over here on the right to where there are fewer holes on the left. So that's why the arrow is pointing to the left. And because holes have positive charge, the hole current is going to the left. Now, what's interesting is you'll notice, mathematically, this is a positive slope, right? It's going, up and to the right. So from our graph here, the current density, remember, is actually pointing to the left. So the current density we pick up a negative sign here. It's minus dP dx, all right? So the other thing, so we've got the diffusion current is proportional to this gradient here, either dN dx or dP dx, but it's also proportional to something called the diffusion coefficient, or another word for it or name is diffusivity, and it's given by the letter D, uppercase D. The diffusivity just describes how fast and far the carriers diffuse, okay, when they're undergoing diffusion. So here are the equations for diffusion current density. So for electrons, J sub n is equal to Q. Now that we have to have a charge in there because we're talking about electric current. So that's the electron charge. And here's dN dx. This is the gradient or the slope in the electron profile. And then here d sub n is the diffusivity of electrons. Okay. Likewise for holes, Jp is equal to Q times diffusivity of holes times dpdx, and remember we picked up that minus sign because of the opposite direction of the hole current and the slope there. So one thing we can do, and we're really not going to use this per se in this course, but technically the total current density in a semiconductor is there may be both types, drift and diffusion, present. So this, the expression on the left, this left term is the drift current term for electrons and for holes here. And then the expression on the right, the last term, is the diffusion current, which we just talked about in the last slide. So that's all this, this sort of combines our results and puts it all together in one equation. But for this course, we're really going to be dealing with one or the other of these, and it'll just depend on the type of application that we're dealing with. So there's something called the Einstein relation, and it leads to another important concept that we're going to see very often. It's actually a constant called the thermal voltage. So we've seen that for current, if we have diffusion current, we're talking about diffusivity, right, D, or it's sometimes called the diffusion coefficient, D. And for drift current, it depends on the mobility, mu. Well, Albert Einstein actually figured out that D and mu are related to each other, and so that's why it's called the Einstein relation. And it sort of rhymes. It says that D over mu is equal to KT over Q. All right. Now, what are these constants? So K is Boltzmann's constant, and you may have learned about it if you took, for example, Physics 203 and you studied thermodynamics. Okay, it's a very fundamental constant in nature. Q, again, that's the one down here, is of course the electron charge, and that's 1.6 times 10 to the minus 19 coulombs. Okay, T here is the absolute temperature in kelvins. So this KT over Q term shows up quite often in semiconductor physics, and it has the units of voltage, and it's called the thermal voltage, VT. All right, and the reason for this is that KT up on the top here is the characteristic thermal energy for each particle in a system at temperature T. And again, this comes from basic thermodynamics, which you may or may not have studied if you took Physics 203. Specifically, there's something called the equipartition of energy theorem, where each degree of freedom for a particle has an average energy equal to 1/2 kT. So if we have an electron that can move around in 3 dimensions, its average energy is going to be 3 times 1/2 kT, or 3/2 kT. So the idea here is that kT is, gives us the approximate thermal energy of an electron or a hole at a given temperature. So that's why this term here, KT over Q, which has the units of volts, is called the thermal voltage. It depends on the temperature T. So what is the value of VT? Well, it's very important, and we're going to use it over and over in this course. VT, or thermal voltage, is equal to approximately 0.026 volts, or 26 millivolts at room temperature. All right, and so we're going to see this. We're going to use this value quite a bit. So going back to the Einstein relation, it says that the relationship or the ratio of D to mu, all right, diffusivity to mobility, is equal to the thermal voltage, or 0.026. So let's see how we can use this now to calculate diffusivity. So we can estimate diffusivity by finding the mobility from a graph like this. All right, so for example, let's say we have silicon doped very lightly with boron at 1 times 10 to the 15. All right, well, if we look at this graph very carefully, 10 to the 15, so this is down here, what's plotted is the total dopant concentration, and up here is the mobility. And so we sort of saw a graph like this before. Remember, the mobility is really large. It's around 1400. up here for low doping, and then it drops as the doping increases. So at 1 times 10 to the 15, we're right here. And if I trace this up here, it's a little tricky to see, but I estimated it as about 1375 for this value right here, okay? And for holes, again, at 10 to the 15 would be right here, and that's approximately 475, okay? So using the Einstein relation, D over mu is equal to KT over Q, I can calculate the diffusivity of electrons is equal to the mobility, mu, which we said was 1375. We multiply it by the thermal voltage, right? KT over Q is equal to 0.026, and I get 35.8, and the units for diffusivity are centimeters squared per second. Okay, so that's how we can calculate diffusivity. Likewise, the diffusivity of holes is equal to the hole mobility, which we estimated to be 475, and we multiply that by the thermal voltage 0.026, and we get 12.4 centimeters per second. Now, what about part B is what about silicon doped with boron, again at 1e15, but also arsenic at 2 times 10 to the 18? Well, remember this plot here is the sum of the donor and the acceptor density added together. Now, 1e15 is, very small compared to 2 times 10 to the 18, right? It's something like 500 times smaller. So we can ignore the 10 to the 15. Let's just use the 2 times 10 to the 18 because that's going to be the approximate value. And so we get, we're somewhere over here on the graph. And so if we go up to this point here, I estimated the value, if you take it across at 225 for electrons, and for holes, again, we're somewhere down here. I estimated at about 110. All right, and then again, the diffusivity is just equal to the mobility times the thermal voltage. So for electrons, I've got 225 times 0.026 is 5.8. And for holes, I've got 110 times 0.026 is approximately 2.9. Okay, let's now shift gears and talk about excess carriers in semiconductors. So just a quick review. Remember in part 1, we learned about these two processes called generation and recombination. Generation is the process in which an electron hole pair is created either by thermal or optical energy, where one of these electrons down here in the valence band jumps up into the conduction band, right? It obtains that energy from either thermal or optical means, and we end up with an electron hole pair, right? We've generated an electron hole pair. And then conversely, if this electron jumps back down into the hole, all right, that is called recombination. So the electron has recombined with the hole here. Now, everything we've talked about up till now dealt with thermal equilibrium. So remember when, what we meant by that was that there's a rate of generation, right? Electron hole pairs are being generated. Electrons are jumping up into the conduction band. That's G, the rate. And then there's a rate of recombination. That's the blue arrows, where electrons up here in the conduction band recombine with holes down here, and we lose the electron hole pair, right? And that rate, that recombination rate, is called R. And at any given temperature, normally a semiconductor is in equilibrium. These two rates are equal. So, electrons are constantly jumping up and jumping back down, and we end up with this sort of equilibrium condition, right? That's what thermal equilibrium means with a semiconductor. So G is equal to R. What we're going to do in this section is talk about a very important deviation from this equilibrium, where we're in non-equilibrium. And we're going to do, what we're going to do is basically introduce excess carriers that put this thing out of balance. And this is something that happens quite often in semiconductor devices. And in fact, this is the way most semiconductor devices work. So here's another example. This is just before we get into the more of the details. Electron hole pair creation by optical absorption. So here we have a semiconductor. This is the valence band down here. It's almost full, right, of valence electrons. And then we have a conduction band up here, which is almost empty. Well, if a photon of light is shined onto the semiconductor, these valence electrons can absorb that photon. As long as the energy of the photon, h nu, right? This again goes back to physics. If as long as the energy of that photon is greater than the band gap here, this electron has enough energy to jump up into the conduction band. By the way, remember, this is called the photoelectric effect, and this was also due to Einstein, and it's something you probably learned about back in Physics 203. This is also how photodetectors work. All right, and imaging chips, like the imaging chip inside your smartphone camera. When photons of light come into the semiconductor, they excite electrons from the valence band up into the conduction band. So now we've got an electron hole pair. Well, that electron can, bounce around up here in the conduction band, but eventually it will perhaps fall back into the valence band. And in order to do that, remember, energy is conserved, right? So it's going from high energy up here to low energy down here. So the only way it can do that is by giving off energy. So it can create a photon of light, right? And the energy of that photon is equal to this band gap. And so this is how light emitting diodes work. This is the process where electrons recombine with holes and make, basically generate light. So it's a very simple process here, but very fascinating and very important applications. This on the left here, this is how photodetectors and imaging chips work. And on the right is how light emitting diodes and also semiconductor lasers, like if you've ever used a laser pointer, this is how the photons of that laser are produced. So there's a concept called majority and minority carriers that we need to define before we move on to the next material here. So in p-type material, remember, p-type material means the number of holes, p, is much larger than the number of electrons, n. So holes are called majority carriers and electrons are called minority carriers. All right, it makes sense. Likewise, in n-type materials, where you have many more electrons than holes, electrons are the majority carriers and holes are the minority carriers. All right, so this is the simple concept and definition of what is meant by a majority and a minority carrier. So another key concept is for these minority carriers is it's a concept called the lifetime. And this basically tells us how long does that minority carrier last before it's swallowed up and recombines with a majority carrier. We'll look at the process here going forward. So let's do a little exercise here and think about the rate of decay of excess minority carriers. So let's say we have a p-type semiconductor. So that's here. So we have, since it's p-type, we have lots of holes. So in this diagram, holes are designated by these empty circles. All right, basically an electron has left those areas, and we have holes there. Okay. And so, initially there are very few electrons up here because it's p-type, right? It's doped p-type. But let's say at time t equals 0, we flash a bright light onto the semiconductor. And remember what happens when we flash a light on a semiconductor is those photons get absorbed and we create excess electron hole pairs, right, by that generation process. So that's shown here. So we've got, because of that light flash or light pulse, we've got electrons have jumped up into the conduction band. So now we've got, a bunch of excess electrons up here. So the total number of electrons, n, is equal to the equilibrium value of electrons, n naught, plus that we're going to use this symbol delta n, which just stands for the excess electrons. That's all these electrons that we generated up here by pulsing the light on the semiconductor. So now, after the light is turned off, remember, these are minority carriers, right? Because this is a p-type semiconductor. So these minority electrons will start to fall back into holes down here, okay? Because this semiconductor right here is not in equilibrium. We've created an imbalanced situation where we have a lot of excess electrons. So those excess electrons are going to want to jump back down into all the holes down here and recombine. So this rate of recombination that we see in this picture follows a classic decay law. It's proportional to the number of excess electrons remaining and inversely proportional to the average lifetime, or how long an electron lasts. So that means the more electrons we have up here, the higher the rate of recombination there will be. And that makes sense, right? If we have 10 times more electrons than normal, we're going to have 10 times the rate of recombination, just because there's 10 times more electrons available to recombine. So the rate of decay of electrons, of excess electrons, is given by, a rate of decay is dt, right? It's the time derivative of the excess electron concentration delta n. So I have d delta n divided by dt. This is the decay rate. The minus sign here is because, remember, the electron concentration is decreasing with time. It's not increasing. So, this dn dt is a negative quantity. So that's why the minus sign is there. And this rate is equal to the number of excess electrons, delta n, right, that are up here. That's this term right here, divided by this Greek letter tau, which stands for the lifetime, the average lifetime of electron. In other words, how long does an electron last before it jumps down? Okay, so this is the basic decay law here. And, you'll see this equation, something similar to this, if you study, for example, nuclear physics, nuclear decay rates, and things like that. It shows up quite a bit in physics. Now, there's quite a bit of math here, and I'm not going to go through all the steps in great detail, but this equation that we just derived on the last page, this decay law, we want to solve this. We want to solve it for for delta n. All right, the number of excess electrons as a function of time. So to do this, there's a bunch of steps here, but it's nothing that difficult. This is stuff you did in your math class, where you, for example, your mathematical methods class. Basically, I moved the dt over to the right side. I put this delta n under the left side, and then I integrated both sides. And when you integrate, a delta, when you integrate d delta n divided by delta n, well, that's a simple integral, right, that you learn in calculus. That's just a natural log. And so by doing, the math here, we end up with this simple result here. The excess electron concentration, delta n, as a function of time, is equal to, we have a new expression here, uppercase delta n, which is the initial value. That's how many excess electrons we start with at time 0, multiplied by this decaying exponential function, e to the minus t over tau. So all this means is that the excess electron concentration is going to decay exponentially with time. So let's interpret this and try to make some sense out of our result. Here's our result again from doing the math on the last page. This delta n out in front here is the initial number of excess electrons. Now remember, so this is a plot of time down here, and this is our excess electron density. I'm sorry, this is the total electron density plotted in the y-axis. N naught is the equilibrium value. So at time 0, this distance from here to here, This is our excess electron density, delta N, at time 0. And we see that it decays exponentially with time, all right, because of this second part of the solution there. And what's kind of interesting here is that this lifetime, tau, is the decay constant here. It's basically gives us sort of the rate of decay. So we see that most of the excess electrons have returned, back to 0. So we're at equilibrium within maybe 3 or 4 lifetimes. So it takes a few lifetimes, but after a few lifetimes, the number of excess electrons has decayed back to 0. So the meaning of the minority carrier lifetime, you can think of it in different ways. Mathematically, tau is the lifetime is the exponential decay time constant for minority carriers, because we saw that in the exponent we had e to the minus t time divided by tau. Tau is also the average lifetime of a minority carrier electron in a sea of majority holes in a p-type semiconductor. And likewise, for holes, the lifetime of holes is the average lifetime of minority holes in a sea of majority electrons in an n-type semiconductor. So one way to, here's sort of a graphic way to think of this. You can think of minority carriers as a small pack of animals that jump into a pool full of piranhas, right? So, think of like a handful of mice that, are unlucky and they jump into this swimming pool full of piranhas. And there's thousands of piranhas, hungry piranhas, right, in the swimming pool. So lifetime, tau, is the average amount of time that those mice survive before they're getting eaten. Okay, so that's kind of the idea here. We've got these minority carriers. They can't last forever because all those majority carriers are going to swallow them up, by recombination, right? They're gonna swallow up those minority carriers. So the lifetime in silicon can vary from around 1 millisecond for really pure samples to as little as 1 nanosecond for intentionally doped silicon where they want a real small lifetime. Typical values of lifetime are in the microsecond range, right? So these minority carriers don't survive very long, right? They survive for typically a few microseconds and then they're gone. Let's now turn to something that's sort of related. And this is also, has to do with minority carriers. This is something called the diffusion length. So if we think of, again, think of this thought experiment here where we have a semiconductor material and we have semiconductor material and we shine a light on the surface here. And it's a steady light here. Okay, it's not a pulse like in the last examples. What happens here is most of these photons of light are going to be absorbed right at the surface of the semiconductor, and they're going to create a large population of excess electrons. Again, this is a p-type semiconductor, so by shining a light on it, we're going to create electron hole pairs. So we've got a bunch of excess electrons, minority carriers, and they're going to be, there's going to be a large concentration of them right at the surface where the light is hitting. Right, and generating these electrons. So what happens here is the excess electrons diffuse away from the surface, and as they do so, they're going to move. Remember, there's lots of them here. There's very few over here. So diffusion of electrons is going to be to the right. As they diffuse, though, they're going to recombine with holes. Okay, so the resulting electron profile, if you do, all the math, which we're not going to do, it looks very similar to what we just saw versus time. But this is a graph of electrons, not versus time, but versus distance or depth into the silicon. But it looks very similar. We see an exponential decay. As we move into the semiconductor, we see less and less excess electrons because of this, they're recombining with holes. So the equation looks very similar. It's delta n of x now, not n of t. All right, so this is the profile of excess electrons is equal to delta n, which is the number here at x is equal to 0, right at the surface, times this exponential factor, this decaying exponential factor, e to the minus x. Now it's not over lifetime, it's over something called the diffusion length. So this is a characteristic diffusion length, L, that describes how far these electrons can go before they are swallowed up and recombine with holes. So we can kind of, do the same sort of analogies here. What we mean by minority carrier diffusion length, L, is mathematically, L is the characteristic exponential decay length constant for minority carriers. It also represents the average distance that a minority carrier electron travels in a sea of majority holes in a p-type semiconductor before it recombines with a hole. And likewise, LP is the diffusion length for holes. It's the average distance that a hole travels in an n-type semiconductor before it recombines. So again, let's go to our analogy of, remember our poor little mice that jump into a pool full of piranhas? All right, so the mice are the minority carriers, and we've got thousands of hungry piranhas. The diffusion length, L, is the average distance that the mouse swims before being eaten. All right, so this is, a very graphic way to think about what diffusion length means. It's how far these minority carriers can travel before they recombine with the majority carriers, which, there are lots of. So this slide is going to show the relationships between some of these um, parameters that we've been discussing. And specifically, we're talking about mobility, diffusivity, lifetime, and diffusion length. So just to remind you, mu is the mobility, d is the diffusivity, tau is the carrier lifetime before recombination, and L is the mean diffusion length of carriers before they recombine. So we learned that d and mu are related by the Einstein relation. So d over mu is equal to kT over q, but we call that the thermal voltage Vt, which, by the way, shown down here, is 0.026 volts. The other expression here we haven't seen yet, and we'll actually derive this, we'll show it's where it comes from in the next chapter. But for now, all we need to know that L, the diffusion length, is related to the diffusivity and the lifetime by this equation. It's equal to the square root of the diffusivity times the lifetime. So the typical use of these equations here is we usually figure out mu first from the doping level graph, and we did that in a few of the previous examples. Once we know what mu is, we can calculate diffusivity by using the Einstein relation. Okay, so we can move the mu over to the right side, and we did this in those previous examples. D is just equal to mu times Vt. And then the lifetime is typically measured or given to us. All right, and we'll do an example on the next slide. So that's something that we can't really calculate per se, but we're given that information. Once we know the lifetime, tau, and the diffusivity d, we can just take the square root of the product, and that gives us the diffusion length L. So here's an example where we're asked to estimate the mobility, diffusivity, and diffusion length for minority carrier electrons and holes in lightly doped silicon, doped at 1 times 10 to the 15 at room temperature. And we're told that the lifetime is 10 microseconds. So at the doping level of 10 to the 15, we did this before, that's right here, we can read off the graph and estimate the mobility of electrons is 1375 up here, and the mobility of holes is about 475 right there. And the diffusivity comes from the Einstein relation. All right, so D is equal to mu times Vt. So remember, Vt is the thermal voltage, 0.026. So plugging in the mobility, multiplying by the thermal voltage, we get for electrons 35.8 and for holes 12.4. I believe these are the same numbers that we used in a previous example. Now, the next part is to determine the diffusion length. Well, the diffusion length, L, is equal to the square root of d times tau. So for electrons, the diffusion length is going to be 35.8, right? That's this number here for d. And the average lifetime is 10 microseconds. So that's 10 times 10 to the minus 6 seconds. You have to convert that to seconds, okay? And so multiplying these two together and taking the square root, you get 0.019 centimeters. Typically in semiconductor theory, we use units of microns, and a micron is a millionth of a meter. And so that would be this number multiplied by 10 to the fourth. Okay, and so, it becomes, I've rounded this a little bit, but it ends up being 189 microns. Likewise for holes, again, we take the square root of the hole diffusivity, which was calculated to be 12.4 times 10 microseconds, and we get 0.011 centimeters. Converting to microns, we multiply by 10 to the fourth. Remember, a centimeter is 10 to the minus 2. A micron is 10 to the minus 6. So there are 10 to the fourth microns per centimeter. So that's how this number becomes 111 microns. All right, the last example here in these notes, it's the same type of example. The only difference is now the silicon is heavily doped. And so the doping is 2 times 10 to the 18, which again is over here. Now remember, we did this in a previous example. The mobilities are much lower, 225 and 110. So the diffusivities are also much lower. I won't, I'll let you go through these on your own, but we already did these on a previous problem. We have 5.85 for electrons and 2.86 for holes, the diffusivity. And then to calculate the diffusion lengths, again, we're just going to use square root of d times tau. Now this problem, we're told that the lifetime is 1 microsecond, so that is changed from the previous problem. So we have for electrons, the diffusion length is 5.85, that's d, times tau, which is 10 to the minus 6 seconds, and that's 0.0024. And, if you multiply that by 10 to the fourth, you get 24 microns. So obviously, for heavily doped silicon, the diffusion length is much shorter. Okay, and that makes sense. There's just going to be more majority carriers for recombination, and so the minority carriers are not going to be able to diffuse as far. So that's why L is smaller. And here's the resulting calculations to figure out the diffusion length for holes. You can just see I plugged in the numbers, 2.86 here, and there's our lifetime again, and came up with 17 microns. So that is our discussion of semiconductor theory. These two videos, parts 1 and part 2, pretty much cover what we need to know about the semiconductor material, but we're just starting to scratch the surface here because we haven't talked about anything practical yet, such as a device. And so, our next step in the course is to talk about how to build something practical out of these semiconductor materials. And that's when we're going to learn how to make PN junction diodes and how to make transistors. So that'll be the subject of our next chapter. Until then, take care and goodbye. Thank you.